Okay, I'll start by taking a look at 14-94. Okay, this one you have a quarter circular tube of mean radius, contains a smooth chain that has a mass per unit length of MO, M0. If the chain is released from position shown, determine its speed when it emerges completely from the tube. Okay, so you have this chain inside here, and then there's a tube. You can barely see it here. And so you release this chain, and then it slides down and has some velocity, essentially, from it when it finally leaves the basically this part here actually gets out of the tube. Okay, so this is a conservation of energy problem, right? So initially, um, there's no kinetic energy associated with this chain. There's only potential energy, and at the end, depending upon uh, where we define our datum point, in this case, it'd probably be good to define it right along the horizon here, uh, is that at that point, now you'll have zero potential energy. So you have some initial potential energy associated with it, and that gets converted completely over to kinetic energy to have the chain moving along in this direction. Okay? So really, the key point here is to come up with the really to determine the potential energy in this chain. Okay, so that's what we'll be looking at in this particular problem. And then it's just a matter of applying the um, conservation of energy uh, formula. Okay, so for here we're looking for V2, right? Basically the point or the velocity when it has left completely out of the shield. Okay. So we have some things that are given. We're given a radius of r, circular radius of that curvature, and we're given a mass per unit length. Okay. We also defining it as being frictionless. Okay. So what that's really telling us is it's following the law of conservation of energy. They're all conservative forces, right? So whatever energy we had initially, in terms of potential and kinetic energy, we're going to have it at the end. The total potential and kinetic energy initially is going to equal to potential and kinetic energy final. Okay. Now, first thing we do is look at the diagram here. So if we gave a quick diagram, not the best sketch here, but basic idea is we want to find the location of the center of mass of the center of mass. Okay. Well, we can apply calculus to go do that. This is just an arc, a quarter arc. Um, we can apply calculus to actually figure this out, but we really didn't talk about that at all. So what you can do, this is a well-known shape. You can actually just get it from a table. Get the centroid of a quarter circle arc. Okay. So in this case, it's just 2 over pi, or in our case, 2 times r over pi. So whatever the radius divided by pi. Okay. So this gives you the centroid of the center of this arc. Okay. So relative to something. Well, and this would be relative to what we might call the 0 point here. So this is just 2r over pi relative to this position here. Okay. What we're looking for is the h. Well, we know the overall distance from here all the way down to here is r, right? Because it's the same as this radius. So h1 is just basically this r from here to here minus 2r over pi. Okay? So that's one of the things we need to recognize to come up with h1. All right. Then the initial of potential energy associated with the oh, sorry, not the. This is not a potential. This is the velocity, initial velocity. Initial velocity associated with it, the chain in the initial position is equal to 0. Okay. All right. So those are what's given. Initial velocity 0. All right. So we're going to use that information. All right. So here's our conservation of energy. Kinetic energy in position 1 plus. This is not this v. This is the velocity v. Should write a little, make it a little bit better symbol here. I even confused myself for a moment there. So this is our initial kinetic energy. Initial potential energy is going to in our first position when it's released is going to equal to the kinetic energy plus the potential energy in position 2. Okay? Well, one of the things we recognize is there's no initial kinetic energy, so that part is 0. There's no, here's the, just written out. There's no final potential energy, so that's 0. So our equation really just simplifies to initial potential energy is equal to the final kinetic energy. Okay? All right. So one of the things we could do is we can actually come up with the mass. And the mass is just, this is the length, right, of our line, right? It's pi over 2 because 2 pi r would give us the length of the whole thing. So this is 1/4, so it's just pi over 2 times our mass per unit length. So this would give us our total mass, right? Our potential energy where we actually start is just whatever that mass is, which is, this, times gravity times h1, okay? In h1, we're going to make this substitution here. It's just going to be, we can write it like this if we want. That might be a little simpler. This is the way the author chose to write it. So it's r times pi minus 2 over pi, okay? Or just r minus 2r over pi, okay? All right. So now what we can do is just substitute this into our equation. So what do we have? And I started to write it out here. I just crossed it all out, really, because I don't need to write that out. You actually don't, it doesn't even matter what that is, right? This is kind of irrelevant. We didn't need that to solve it because mass will show up on both sides of the equation. We cancel it out, and all we have to do is just solve for V2 then, and it simply just becomes this. So the only really key thing to this is coming up with this center of mass, right? Here, this 2 over pi is really the only thing of I think, significance that you need to do. Just coming up with that center of mass, knowing it's the center of mass you're looking for, and knowing how to come up with that location. Okay, and like I said, we didn't really cover this. We didn't cover centroids and how to go and calculate them. So if there was anything on an exam or quiz, I would give you like the well, there won't be anything on a quiz anymore, will there? Because we already did the last one. But if it's on the final, I would give it to you. I would just tell you what it is because I'm not expecting you to do that part. Okay? So that's it. That's the final answer for this one. All right? And like I said, the mass both cancel out. So it's really irrelevant what the mass that is. Given that it's frictionless, it's really irrelevant. Okay? And that's it for that.